First of all, thank you all for joining this talk, both now and later on YouTube. It is a pleasure to be speaking to so many people about our technology. So today's talk is intended to introduce what this technology is, what it's for, and what it's for in the context specifically of FHE. So I will start with the basics. So we'll introduce us. So who are we? We are Optalysys. We are a deep tech hardware company, and we work in the field of optical computing. Specifically, we engage with a branch of optics known as Fourier optics, which makes us quite unique even by comparison to other optical computing outfits. We are developing a chip-scale photonic computing technology that allows us to bring high-speed transform computing directly alongside digital logic at the SoC MCM integration level. That technology and that degree of integration allows us to address a very significant challenge in information security. So, in the interests of keeping things friendly for anyone new to FHE.org, fully homomorphic encryption, or FHE, is a method of encrypting data in such a way that you can perform valid computations on encrypted data. And that is a short statement with big implications for data protection. Now, we at Optalysys are developing accelerator hardware for this technology, and our focus today is on that hardware and the principles of how it works. But to keep things very brief, FHE allows us to do computing tasks in secrecy. That removes the need to rely on trust when you share data, which has huge implications for the way that data is currently managed and used. Of course, if you're here, chances are you know this and are already interested in FHE, so we won't dwell too long on this. At the very basic mathematical level, the aspect of FHE that enables this capability is that it allows us to add or multiply two pieces of encrypted data together and produce another valid ciphertext that contains an encryption of the correct output. That sounds simplistic, but that property also allows us to construct more complex operations. In fact, addition and multiplication alone allow us to perform any operation that a computer could otherwise perform on unencrypted data. However, that does mean that even basic computing operations that would normally be done directly in hardware now need to be replicated using additions and multiplications. And there is some additional complexity introduced through aspects of cryptography that we will address shortly. For now, though, and certainly from a hardware perspective, it's important to fix in our minds that FHE is predominantly referring to additions and multiplications of encrypted data. So contemporary FHE is a collection of different implementations of the same core cryptographic idea, and these implementations are known as schemes. Now, all current FHE schemes share the same core cryptographic principles, and any given scheme fundamentally allows you to perform any computation that you might wish. However, the way that these schemes are constructed means that they often have certain advantages when used for different processing tasks. And of course, if you don't want to have to build an FHE implementation from scratch, and I can assure you that you don't, you will find libraries that implement these schemes alongside the more advanced utilities that allow you to use them more easily as a developer. So all FHE schemes fundamentally involve addition and multiplication on encrypted data, but there is a fairly significant split that allows us to divide these schemes into two categories. The first is the so-called vector or packed schemes. This refers to the BGV, BFV, and CKKS schemes. In these schemes, you can encrypt or pack multiple values into a single ciphertext, such that whenever you perform an operation on that ciphertext, you perform it on every value at once. This is akin to single instruction multiple data parallelism in GPUs. So these schemes can achieve relatively high throughput on parallel numerical calculations. On the other side of this split is TFHE, where the ciphertext encrypts a single value. So nominally, we only operate on one value at a time, but the performance is more consistent. TFHE also enables a very useful trick known as programmable bootstrapping, which would allow us to use what would otherwise be a wasted process that has to be performed as part of the essential cryptography to execute a useful computation. Specifically, we can use programmable bootstrapping to directly evaluate a single variable or univariate function on the encrypted data, a task that would otherwise have to be performed using many individual calculations in the vector schemes. So here on the left, you have the various different schemes. You have a categorization of the kind of math that they perform. So BGV and BFV, they work fundamentally on integers. These are packed schemes. You have CKKS, which was developed to work with floating point math, and you have TFHE, and then you have the libraries in the middle that provide varying different implementations of these core schemes and some of the platforms and tools that make use of these libraries on the right. So the challenge is that ciphertext representations can vary somewhat depending on the scheme, but there is a significant commonality. Ciphertexts contain coefficients of large degree polynomials, and these are big. So typical ranges for the number of entries in a ciphertext vector can lie anywhere between 1024 to about 65,536 elements. And the precision of these coefficients can reach 128 bits or even exceed that. Again, this is very dependent on the scheme, the security parameters for the computation, and so on, but there is no getting away from it. FHE natively requires a lot of compute. We need arithmetic on large numbers that do not fit well with standard computing architectures, such as your regular CPUs. And a big part of that is large-scale polynomial multiplication. So that is a big chunk of the arithmetic. It is, however, worth noting that the reason why we are performing operations on polynomials is not accidental. It's a conscious decision on the part of cryptographers, as this allows us to leverage a more efficient multiplication method through convolution, which is accomplished through transform operations. These transforms, fast Fourier transforms or number theoretic transforms, depending on whether or not you are working on integer or floating point representations for the ciphertext, when applied to the ciphertext vector, allow us to perform an element-wise multiplication rather than a naive quadratic complexity multiplication. This is because we're using polynomials. So this is naturally the more efficient way of doing things. But now we need to compute a large transform every time we want to do a multiplication, and we have to do that a lot in FHE. Not only do we need to do it for the actual core arithmetic that we want to do, those multiplications, but we also need to perform it as part of the housekeeping operations that are required as part of the cryptography itself. So the most significant example, of course, being bootstrapping. Bootstrapping operation in TFHE, for example, can require about 1,000 high precision 1024 point FFTs and IFFTs. So if we are going to deliver 10,000 times acceleration over CPU, we need to go from tens of milliseconds for a bootstrapping operation down to microseconds. That is an enormous amount of computation that needs to happen very quickly and consistently. And that is only part of the story. We also need to transport and store the massive amounts of data that we need to move as part of this process. So this is fundamentally going to require a specialist architecture if you are going to meaningfully accelerate FHE. So we have to consider that transforms are the predominant bulk of the computation itself, 70 to 90% of the computation, depending on the scheme parameters. And this is where we come to our contribution to this problem. In electronics, the fast Fourier transform is famously an order n log n operation. That's the number of operations that need to be performed to calculate an FFT. It's a divide and conquer algorithm that makes clever use of the symmetry in the complex roots of unity for vectors of a power of 2 length, and that allows us to cut out a huge amount of additional operations compared to a naive Fourier transform algorithm, the discrete Fourier transform. The same thing also holds for the number theoretic transform. So regardless of the scheme and numerical representation for ciphertexts that we are working with in FHE, we still have similar problems. By contrast, light can perform a Fourier transform through an interference process. Crucially, this transform is done at the speed of light and is an order 1 analog process. This operation also generates no direct heat, it's entirely passive. So if we can harness this process as part of a digital workflow, there are some serious advantages to be had, and that has been the objective of Optalysys for about a decade now. And in FHE, we find a pressing need for an enormous quantity of extremely fast transforms, and that is where we shine. So bringing this technology into the digital world has been our preoccupation for nearly a decade now. And over the last few years, we've been moving into silicon photonics, a technology that allows us to integrate optical paths and control components as elements of an optical circuit on chip in much the same way that conventional electronic digital circuits are made. Indeed, one of the key advances that we are taking advantage of is the ability to make chips that feature both silicon photonics and conventional digital CMOS. So this allows us to have a fully digital wrapper around the optics in our system and to use existing high-speed digital chiplet interfaces to make the most of the speed of photonics. Of course, we actually need to translate digital signals into specific optical signals. So for this, we draw on technologies from the world of high-speed optical communications, both to make use of existing and well-qualified IP, and also because the silicon photonic components developed for this task can manage extremely high information encoding rates. So in our ETILE systems, we use these high-speed modulators to write digital data into several optical waveguides that then collectively emit into a free space optical environment, which is etched into the plane of the die. And in this free space environment, you get optical interference, which results in the Fourier transform of the data being projected onto a focal plane, where it is then separated back into individual waveguides and then redigitized. So each free space section, and we can fit multiple of these sections on a single die, is only dealing with a subset of a larger transform calculation. However, given the speeds at which we can calculate, we can still use the same process that generates a fast Fourier transform to provide large, high-precision transform calculations in nanoseconds. That's what we're aiming for. So this is what I am referring to with regards to the photonic transform circuit. So you can see here on the right the general layout of this circuit. So on the left-hand side of this process, you have the incoming laser light, which is split via a tree multiplexer. You then have the individual transceivers that control the light that's passing through these individual waveguides. These encode digital values into the light. This is then emitted into the free space environment here, and this is not what the free space environment actually looks like. It's just a simulacrum. The light then interferes with itself, passing through this free space environment, and is then recollected into these waveguides where you have sets of balanced photodiodes to detect the complex output. And crucially, these can run at extremely high data rates. You can achieve, tens or even hundreds of gigabits per second from existing modulator technologies. And when they are all working in tandem, you can understand how you can actually tear through even a large transform at very, very high speed. So this is something that we do not often show, but this is actually the Benchtop system that we currently have in the lab. So this is all discrete RF components, discrete detectors, discrete modulators, and so on. This is obviously something that we will be co-integrating in a final system, but this chip in the center here, and you can see where the light leaves the system, this is actually one of those free space environments that is on this chip. It's obviously not the entire thing, that would be quite large, but on this chip, I can assure you there is one of those free space environments that we are currently testing, validating, and hopefully should be hooking up to an FPGA so we can drive very high speed RF signals to the chip, have that control modulators, and we can start working with very high speed transforms, albeit through only one of these free space environments. So what's the end goal here? ETILE provides the computing power needed for the majority of an FHE workload. It aims to provide an extremely low latency implementation, and that is, of course, very important for acceleration. However, trying to pass that quantity of information over an interface, such as PCIe, would rapidly present a new bottleneck. So a solution to FHE has to be able to capture most, if not all, of the workload on a single platform, on a single MCM. That means we need to provide the supporting electronics directly alongside the transform compute, and the way to do that is to leverage high-speed inter-die interfaces. In the process, this also presents us with an opportunity to develop the bespoke architecture that we discussed the need for earlier, providing custom arithmetic processing and buses to address the remaining 10 to 30% of the operations that are not transport-based, as well as the intensive memory that we need as well. So collectively, these advances allow us to target 10,000 times acceleration versus CPU, although this will have some natural variation depending on the particular scheme and the parameters that are involved. Of course, FHE acceleration is well recognized in the field as being necessary. So the optical approach gives us something of a unique capability that goes a little bit beyond speed. The way that we reconstruct larger high precision transforms allows us to generate components of either the fast Fourier transform or the number theoretic transform. So that allows us to actually be a universal scheme accelerator. So the work in this section was done by my colleague, Dr. Florent Michel, who found a way to do both NTTs and FFTs using the component calculations that the optics is performing. So some schemes, I should note, use the NTT as part of their multiplication approach, while others, specifically TFHE in some implementations, uses the FFT. So enable is our end goal. And right now, obviously, we are qualifying the silicon photonic circuits that we've actually designed to carry out that core computation. So hopefully enable at the end of the 2-year development process that we have underway right now will provide us with the ability to demonstrate FHE workloads running on hardware that uses the optical transform, and that will mark a major step forwards for the field. So to give you an idea of how we are progressing towards this, we are not just focusing solely on enable in terms of that's the only solution that works. Along the way, we have opportunities to demonstrate not just the technology, but even an advantage from the photonics. So you saw the Benchtop system earlier, in conjunction with an FPGA, which is driving the signals to it, and also handling some of the reconstruction, some of the other FHE operations that are required for a complete workflow. We believe that first system, when working at the speeds we are trying to drive the chip at, will be able to deliver about 5 times acceleration versus CPU. However, the core FHE development that we're doing in terms of the FPGAs, that is actually something that we consider to be useful in its own right. So the next step of things is integration of all of those various RF components that you saw earlier. And the way we are planning to do that as a stopgap is to use existing solutions from the transceiver industry. So if you think about pluggable transceivers in the context of data center data transport, those systems actually already have a lot of the supporting infrastructure that is needed to transfer data to and from a photonic component at very high speed. So the next step is actually to create transceiver type pluggable photonic compute units that can interface with an FPGA over pluggable mezzanine cards. And that would allow us to make a much more tightly integrated system that we could then start to demonstrate some real speed ups on. So we expect a system based on this approach where we'd have multiple individual free space stages involved through each pluggable. We expect that would achieve about 250 times acceleration factor for TFHE certainly. And then, of course, towards 2025, the goal of what we're doing over the next 2 years is to integrate this technology into a single MCM, and that would be sufficient to give us that advantage that we are seeking, that 10,000x acceleration. So this is to give you some idea of what we are talking about. So FPGA systems, you have the pluggable modules that we are planning to build and sort of see sometime next year. We can also integrate many of these pluggable based systems into a data center rack that we can then think about for demonstration in the cloud. And at the same time, we also have the tape out of the Etech and enable as major landmarks for this development. So earlier, we outlined the schemes and the libraries, but working with these things is obviously, a different matter. So our accelerator technology is based on optical computing, but when it comes to FHE, no additional knowledge of optical computing is required to use our system. So we deal with the integration of our technology with existing FHE libraries and tool chains, allowing developers working with these libraries to develop applications that will just run natively on Optalysys systems. And you can see here a map of existing libraries and the platforms that depend on them, as well as our current status for integration with Optalysys hardware. And we do have a particular focus on both concrete and open FHE, as this provides complete coverage over all the FHE schemes that we showed earlier. So integration with these libraries will be supported by our initial benchtop systems onwards. So we are also part of the Phoenix project. So this is an EU project that we are engaged in conjunction with the UKRI, for example, with IBM, Lumiphase, Leuven. So this is focusing more on the technical side of the photonics. So the objectives of Phoenix are to test novel photonic systems made using new materials, vanadium oxide and barium titanate oxide, I believe, to develop new waveguide platforms and test out new modulator technologies, and to build up demonstrator systems. So alongside FHE, the Phoenix project is also thinking about other applications of very high-speed Fourier transform processing, such as 5G infrastructure and neural network training and inference. And indeed, the poster we submitted to FHE.org in 2023, this was something that we referenced as well. So I think that's the span of my presentation. I will now open things up to questions. Remember, it's not just myself, there is also my colleagues as well in the chat, so we should be well placed to answer any questions that you have. Thank you.
Okay, thank you very much for the interesting talk, Joseph. Yeah, do we have any questions to get us started? Okay, we have a few in the chat. So those who've posted in the chat, maybe one of you wants to unmute yourself and ask a question. We have one from Stas. Do you want to unmute yourself and ask?
Hello?
Hello.
Hello. Can you hear me?
Yes, I can hear you.
Super. I'm Stas Polanski in Ganyama. That's startup accelerating a similar type of computations, but electronically. So I do have some experience with silicon photonics, and maybe it's kind of obsolete, but to my taste, like it's all optical. We have 8 bits, right?
Mm-hmm. Yeah.
And we're talking about entities with hundreds of bits. So there is a gap between what we have now, like 8 bits in analog FFT, and 128 to 56 bits required for your cryptographic primitives. Yeah. So how are you going to, like, my question is, how are you going to bridge this gap?
It's a very good question. So we are fully aware that we need to go from notionally very low precision optical computing to very high precision in the same way that you would get from an electronic system. Now, fortunately, the Fourier transform is itself a linearly separable calculation. So you can actually do this bitwise. So we can use low precision silicon photonics to build up both the span of the vector and also the precision. So Florent did a lot of the initial work in this space. And we have actually some details on Medium, which are now slightly outdated about how we do this precision reconstruction. But the long and the short of it is that in conjunction with the memory architecture that we have, we can feed information through the system on a bitwise or word basis, and then recover a high precision transform on the other side.
Well, do we have anything published on this? Because again, to be honest, I'm kind of rusty on this stuff. So it would be easier if, like, your patents or your scientific articles to explain how you can kind of partition LSB, MSB, and then put everything together. Because so far, like for me, it's a mystery right now. I don't understand.
Yeah, so we do have some material out there. It's not a published scientific paper, but we do have some material out there that explains how that works. Laurent, if you're in the room as well, it might be worthwhile you covering some of this as well. If that's okay.
Yes, sure. So yes, as you mentioned, we have some Medium articles showing actually an earlier algorithm that we used, which is quadratic in the accuracy. Yes, I don't have the link at hand right now, but I guess I can send it to you later. So that's actually an easy way to reconstruct higher precision, either for a transform or entity, which is quadratic in the target accuracy. We now have a more efficient algorithm, which is either linear or non-linear in the accuracy, which I think we don't, thanks Joe for the link. I think we don't have anything publicly available on this algorithm, but yes, I mean, if you're interested, please get in touch and we can. Yes, I would need to check with my colleagues what I can disclose or not without an NDA. But yes, we're happy to.
Yeah,
happy to discuss what I can.
It's something we are playing quite close to our chest because it is very important to this. I mean, it's one of those things where you can empirically verify that quite easily that the process works. It's just not something that we necessarily publish. So it's something we discuss more under NDA.
Yeah, so just let me try to summarize what I understood. So you do have some mathematical tricks to take care of this mismatch between low accuracy of analog optical computations and the requirements of cryptography, like 256.
Yes. Yes.
Absolutely, yes. Yes, essentially you can using specific properties of the Fourier transform or the entity, you can decompose one high accuracy computation into a set of many low accuracy computations. And then essentially we use the speed of the optics to do all these many low accuracy computations very fast, and then recombine the results to get a single high accuracy result.
Okay, fair enough. Thank you.
Thank you. Okay. Should I just move to the next question in the chat? Was that Zayan Shi?
Sure, yeah.
Yes.
Yeah, I was curious how does the free space environment work? Like where the light interferes with itself? What is it made of?
So a free space environment is exactly what it sounds like. It's an environment that light can propagate and interfere. So you have multiple sources of light all emitting into one space. So it's exactly like if you think about you ever done a Fraunhofer diffraction experiment?
I have not. Is it kind of like a standing sound wave in a tube or something?
Yeah, it's where you illuminate a single narrow slit with coherent laser light, and what you get projected at the focal plane of that is a sinc function, which is itself the Fourier transform of a step function, like a slit. So in the space between the slit and the focal plane, if you go by Fresnel's sort of method, where you think of each individual point along that slit as emitting a single radial source of light, and then all those radial sources of light are of course interfering with each other, then that is a free space environment. That distance over which you are propagating the light is the free space environment. So in terms of how it works, I mean, there's the understanding of like optical free space, and then there's the specific implementation on the chip. So in terms of how it works on the chip, then it is just effectively, a void that light propagates through. It is shaped such that we don't need to include a lens to refocus the signal. Instead, it's actually in the properties of how we curve the walls of the free space environment. But that's how you do it in one dimension in silicon photonics anyway.
Cool.
Benoit?
Yes. Sorry. So you said you can calculate a Fourier transform with 0.1 speed.
Yes.
And your sensors, I believe they are sensitive to intensity, not the amplitude of the electric field. So
Yes, sorry, carry on.
Yeah, no?
Yep.
So
Yes, so the balanced photodiode, so that actually you can perform complex recovery from both amplitude and phase.
you can recover the amplitude immediately.
Yes, from the detectors on the at the end of this process, yes.
Oh, really?
Yes. And then you quantize that.
Because usually, if you do Fourier optics, you got the source in the object plane. You pass it through a lens, then you recover the Fourier transform on the image plane, focal plane.
Yep.
And but sensors are usually sensitive to the intensity, which is a square. Then so you would have to make a square root calculation, which would take log n operation to do it.
In terms of how that signal is recovered, I don't believe we need to. Now, that's something I would have to check in more detail with the Photonic. Florent, go ahead.
Yes, well, I also don't know the details of how it works, but at a high level, I don't know if you're familiar with the concept of homodyne detection.
Maybe
yeah.
Long time.
Well, it's essentially to make a very long story very short. Detectors use essentially they use interference between the result and some reference signal to get the phase. Yes, essentially, just if you detect both the amplitude and then the amplitude, after you will combine the signal with some reference signal, which has a known phase. You can easily see that you have enough information to reconstruct the full complex number. And yes, you can show that you can do that in a way that actually essentially you can combine the result with some reference light beam in two ways. One of them will give you the real part, and the other will give you the imaginary part.
So that's why you said that you recovered the full potential in the previous presentation, like because I found it very surprising. Because usually you don't recover the potential, you can recover variations of the potential, but
exactly.
Okay.
Yes, that's a very good point, and that's actually exactly how these detectors work. Because yes, just like the potential, the phase, the complex phase is not unobservable, it's not being observed. But if you have a reference beam, and you say that by definition this reference beam has a phase of 0, for instance, then can combine this reference beam, so takes the sum of this reference beam and the result. You get the value, and then takes the difference with some dephasing.
Okay.
Yes.
And I have another question. So not in that presentation, but the previous one also, you said you were limited by two-dimensional Fourier transforms. Here you make just, for the application, you make only one dimensional Fourier transform. But I believe you can combine several 2D, if you combine three 2D Fourier transform, there is a technique to reconstruct a 3D Fourier transform. So maybe you can...
Yes, there is. You can absolutely go from varying sort of like dimensionalities of Fourier transform to higher dimension, and you can actually go from higher dimension back down to lower dimension as well. So where we came from with this technology was the field of machine learning, specifically convolutional neural networks, which require a two-dimensional transform because you are doing a convolution over a two-dimensional grid. And we actually moved from that application to FHE because at the end of the day, both applications need convolutions. It's just how you think about it. We have moved to a one-dimensional scheme purely to make it easier. And the choice of the number of waveguides in and out from the free space environment is chosen to make it specifically easy to go to powers of 2. In terms of the calculation, so that cuts out, a lot of excess computation that might otherwise be necessary.
Okay. Thank you. Thank you very much. That's it.
No, that's excellent. Thank you.
Okay, I can read the next question out. So it's from Dahlia. So is the support for OpenFHE on all schemes or just TFHE?
So the support is for all schemes nominally. So obviously there will be differences, quite significant differences in the schemes and the parameters that they handle. So in some cases, things like CKKS, BGV, for example, there's probably going to be different usage of the memory, for example. There's going to be limits to the actual memory on the chip as well. It should be sufficient for the operations you want to perform in FHE, but there are going to be considerations there. So in terms of open FHE, what we foresee for the near future, and this is a trend we foresee in FHE in general, is the use of leveled schemes for those operations. So leveled BGV, leveled CKKS, without the extremely intensive bootstrap. The system will be capable of doing that, but that will obviously, result in a bit of a ding to the acceleration, because you can't perform the bootstrap like you do with TFHE in a very sort of efficient operation entirely on the device. So that is a trade-off that we're making, certainly for the initial enable system, but it will still deliver quite a significant acceleration to those schemes. We need to actually assemble the system before we can benchmark that, obviously. But yes, we do intend to support all the different schemes through OpenFHE. Okay, sorry, next question then.
So next question is from Guowei. Guowei, do you want to unmute?
Yes. First, I'd like to thank you for the great presentation and using the performing the Fourier transform using Optics is actually great, a very brilliant idea. And I mentioned and I noticed that your system supports both FT and NTT, which is another commonly used scheme transform in the FHE schemes. So I'm very curious about how you achieve NTT using Fourier optics. Like the NTT works on the integers and it requires the modular operations, which is quite expensive in electrical devices. And I'm quite curious, how do you deal with those modular operations?
So this is very much more a question for Florent, because he's the guy who developed the actual process for this. As to how we do that, I'm not entirely sure if that's something that we require an NDA to discuss in detail, because again, that's quite a core part of our advantage. Is there any light we can shed on that, Florent?
Yes, I think you're right. Yes, we need to check with Nick what you can say with NDA. But yes, I think what we can say at a high level is that essentially the accuracy build up mechanism to the algorithm we use as you want to reconstruct a higher accuracy Fourier transform can also be used to convert between Fourier transform and an entity under some conditions. So yes, to mention what I can tell without NDA, the accuracy build-up algorithm essentially can be used to convert a sequence of small Fourier transforms to entities, which can be used in the construction. So regarding the another thing which I think I can tell is that so you mentioned modular reduction. So this will be done on the electronic side. So we are not doing modular reduction on the optics. We do them on the digital part of the chip.
I see. Yeah. Oh, thank you so much.
Yeah. No, the supporting electronics obviously is designed specifically for FHE, and indeed, because of the way that FHE works, the way it's precompiled, the way it follows like a preset circuit, effectively means that the system is in some respects actually quite simple. It is solely dedicated to the supporting arithmetic operations, with obviously some kind of state machine controller. But because everything can be pre-compiled and there is no flow control at all, then this is where we see the potential to deliver quite a significant advantage.
I see. Yeah. Thank you so much.
No problem.
Okay, and another question from Zion Sheep.
Yeah, at the beginning there was like an acronym that you said kind of fast, SOCMTM. What does
Sorry,
the MTM mean?
MCM, so multi-chip
Oh,
module.
Okay.
Yeah. And I believe your earlier question as well, which talking about in the chat, was how do you make circuits with light? How do you make transistors? And the answer to that, and for the benefit of obviously people watching later or who came a bit later, was we don't. Optical transistors are still something that is a little bit far off in the future. They would obviously be very fast, very powerful if they existed. But what we are using here is an analog physical phenomenon that happens to produce the correct output that we are looking for. So we are leveraging that rather than leveraging transistors to do these calculations. And then another one from Benoit here as well.
Yes, but I wrote it, so maybe I don't need to repeat it.
When you are in
Okay.
a 2D system, are you limited to separable functions? Do you mean in terms of the transforms?
Your source, I guess it's on, you can consider it's on a 2D matrix.
Mhm.
And so maybe, yes, the functions at the beginning, at the entry, might be separable, but maybe I'm wrong. Maybe you can do any functions you want.
Sorry, go ahead, Florent.
Maybe you can do any functions you want, I don't know.
So do you mean using the optical system?
Like if you have f of x, y,
Mhm.
and you transform it to FUV, are you limited to fxy equals fx times fy? That's what
I think I see what you mean. Not necessarily, no. It's, well, ultimately we can do any FT-based, for instance, can do 2D convolutions, which, if I'm not mistaken, are not separable.
Okay.
Unless I'm missing something. So no, essentially, yes, for us, the criterion is more whether the function is mostly FT-based or not. So since, as you mentioned, our core technology really performs the Fourier transform, so we can do efficiently everything which heavily relies on Fourier transforms.
It's not about the optics part, but more about the source. Like maybe the source is constraining the type of function you.
Okay, I see what you mean. Yes. Yes, that's a good question. No, in this case, we are not limited. What we do is so the input is discretized, and as you can see it as a set of pixels, and we can set each pixel to an arbitrary value, since we don't have any constraint on the relative values of the pixels.
Okay, but the pixel is not smaller than the wavelength. I guess it's not possible.
No, yes, it is significantly larger.
Okay.
Yeah. There's a great one from a Cyan Sheep here, which is okay. To Cyan Sheep, do you want to go ahead?
Yeah. Like, what is the theoretical physical limit of information you could possibly fit into a free space environment and like actually measure or calculate FFT with a measurable result?
So where we came from before we started doing silicon photonics, where we were doing work previously is, if you're familiar with the old sort of optical correlator system, so this is a technology that kind of came from the 1960s, is that these were entirely analog systems. And what we were doing previous to this, especially in the fields of things like genomics, where you're not looking for extremely high accuracy, you're looking for convolution, you're looking for individual points of light. We were able to fit millions and millions of data points into a single calculation through the use of spatial light modulators. So this is kind of before my time. I'm kind of talking about Optalysis in general. So the FFT is order one. It's completely indifferent to the amount of information that you fit into it. As to how much information could you possibly fit into a single free space environment, it'll be a lot. I don't have an exact figure to hand because nobody's ever actually asked that question, at least of me, but it will be significant. Florent, I mean, if you have any input on this one as well, that's an interesting question. But yes, you could fit a truly massive FFT into free space, even a very small free space environment, as long as you had the dynamic range on the output. That would be your primary limiting factor.
So is the limit here not necessarily light frequency, just like the size of the environment, or?
Yeah, I mean, really, the limiting factor is the speed at which you modulate. That before you hit any kind of quantum physical limits, the speed at which you can actually change the input field is your limiting factor to the rate at which you can compute. So I guess
I didn't
that's
even think of
probably
that.
yeah, exactly. This is why, there's two ways you can go with optical Fourier transforms. You can go very, very large and make real use of that O1 operation as long as your application supports it, or you can use that as like multi-terahertz carrying capacity of like for things like on-off keying. You can go incredibly fast. And we go incredibly fast and very small.
I guess we're probably not going to be making like light frequencies with like at the Planck limit. So
Yeah, I'm afraid the amount of energy you would need to get down to frequency limits like that, absolutely enormous. Yes.
so like 1,000,000 bits would be a good near-term max.
Oh, you could get 1,000,000 bits into a free space environment. Yes, it depends on how you actually control your input field.
Cool.
Yeah.
Okay, thank you for the great questions, everyone. Do we have any more questions before we wrap up? No, if not, then I'm sure I speak for all of us here when I say that I appreciate Joseph for taking the time today to give the talk, and Florent for the answers as well, and everyone from Optalysis who joined us today. We appreciate you taking the time. I'm going to post into the chat the link for our Discord server. So we have lots of discussions on there, and we can always follow up afterwards with questions about this meetup. And as usual, the resources will be posted online in the next few days so that everybody who's not here today can benefit from those. Until the next meetup, thank you, everyone. And just as a reminder, we're going to stick around for 5 to 10 minutes and turn the recording off and just have a little casual chat if anyone wants to stay around for that.
Thank you.